Okay, video 1 of 2 to make up for the lecture that we're missing next week. This is our first video on Chapter 8. So Chapter 8 is really just a continuation of Chapter 7, where we're going to keep thinking about quantum mechanics and then kind of scaling up and thinking about atoms on the whole rather than just subatomic particles. Alright, so in this video, we really have two objectives. The first thing we're going to do is learn the fourth quantum number. It's really an easy quantum number. It's not a big deal. Once we've learned that, we're going to use all those quantum number skills, and we're going to start building orbital box diagrams. It's an important skill to figure out magnetism, so we're going to talk about that a little bit. But these are the two skills, so I'll try to not talk too much and be quick. And then you can watch video number 2. Okay, so we said in the beginning of Chapter 7 that we need 4 quantum numbers to give the full address of an electron. So we know 3 of the quantum numbers, right? We know the principal energy, the angular momentum, and the magnetic quantum number. We've reviewed what they mean, but it's shown there on the slide if you want to review. And we've also talked about how you can assign them from electron configurations, which we're going to practice in the second slide, or in the second video today. But those are the 3 that we know already. The new 4th quantum number is called spin. So it turns out that when you put 2 electrons together in an orbital, they can't spin in the same direction. We'll talk a little bit about why. So they have to have opposite spin. Now we could have used any number. We could have used +1 and -1. We use the different sign to indicate a different direction of spin. But instead of using -1 and +1, they've chosen to use 1/2. So the spin quantum number is really limited in what it can be. It can either only be +1/2, that's a possible quantum number, or it can be -1/2. And that just indicates that we have 2 electrons spinning in 2 separate directions. So here's everything about quantum numbers, but shown in pictures, not in words, just in case that's helpful. The principal energy tells us the size. The angular momentum tells us whether we're in S, P, D, or F. The magnetic quantum number, of course, tells us which room we're in. So each of these subshells have different numbers of rooms, and so we have to number the rooms. That's what the magnetic number does. And now we know that once we're inside of an orbital, let's say we're inside of an s orbital, which is a sphere, we can have 2 electrons in any orbital, and now we know that one electron is going to be spinning in one direction, and the other electron has to be spinning in the other. They have to have opposite spins. This is a lot like magnets, right? And magnets are related, and we're going to talk about magnetism in a second, but magnets are related to electron spin. So if we try to take a magnet that has a north pole and a south pole and push it together with another magnet, and we line up the poles, oh boy, that doesn't look like north, right? And we line up these poles, we know that these magnets are going to repel. They're not going to want to line up. We all did this in elementary school, right, where we chased the magnets around and they wouldn't attract to one another in this configuration. Much like if we had an electron spinning in the same direction inside of an atom, they would repel, and our atoms wouldn't be stable. They'd all kind of go blowing apart because the electrons wouldn't be attracted to one another. But because they spin in opposite directions, it's like lining up a north pole to a south pole in a second magnet. So these magnets would feel very attracted to one another, right? And in fact, sometimes they're hard to peel apart from one another because of that attraction. That magnetic attraction comes from the fact that electrons spin in opposite directions. So that's our 4th quantum number, and we'll use that in the second video, but I'm just introducing it here. So that's your 4th quantum number. If I wanted to give you a series of 4 quantum numbers, right, I could tell you that we're in the 4th energy level, in the S subshell, in room 0, and I could tell you I'm talking about the positive spinning electron. That is a good set of quantum numbers. This is possible. All right, the other day in class we talked about possible and impossible quantum numbers. That's a legit set of quantum numbers. That's the 4 quantum numbers I would need in order to talk about a particular electron. So we'll practice this, as I said, in the next video. There's a picture of spin, in case these pictures up here don't make any sense. These are electrons spinning in opposite directions, creating a north-south and a south-north orientation. Okay, so now we're going to take all this information that we know about quantum numbers and electron configurations, and we're going to build orbital box diagrams. So I've taken this picture here. I've actually flipped it upside down. This is this is showing us the shape of s, p, d, and f orbitals, right? So in the s subshell, there's one orbital. In the p subshell, there are 3 orbitals. In the d, there are 5 orbitals, and in the f, there's 7. We've gone through this before, so I'm going a little bit quickly here, but look back at your notes if you need a refresher. Instead of drawing all these crazy shapes, these dumbbells and, flower petal shapes, the D's and F's get really complicated. We use box diagrams to denote those orbitals. So in the S subshell, if I want to talk about its one orbital, I just draw one box. For the P subshell, if I want to talk about its 3 orbitals, I just draw 3 boxes. This box is showing me a really simple representation of this orbital. All right, so they're just highly simplified pictures where we can understand how many orbitals there are and how many electrons they can hold. You are not going to be responsible for identifying these shapes in F and D, but you do need to know what S and P look like. S orbitals are spheres, and P orbitals are these dumbbell or flower petal shapes. Some people call them peanuts, but it's this oblong, double-lobed shape. So you do have to know these on site, but you had a question like that in your practice packet the other day, so you kind of know what those questions look like. Okay, so if I wanted to draw an orbital box diagram to reflect nitrogen, nitrogen has 7 electrons, and this is its electron configuration, 1s2, 2s2, 2p3. So for every subshell, I need to write or draw the appropriate orbital box diagram, right? So these are the box configurations I could show, and now I need to show a box for 1s. So any s gets the 1 box. So 1s and 2s get boxes like that. And then if I want to draw a p subshell, I need a set of 3 boxes. So I'm just borrowing from S, P, D, and F box pictures up there and making this electron configuration. Now, how I put these electrons in. I know that I have 2 electrons that need to go into 1s. I have 2 electrons I need to put into 2s. And I have 3 electrons that need to go into 2p. In order to put in the electrons into this picture, I have to follow a set of rules. There are 3 rules that we use to place electrons. The first rule, it's called Aufbau principle. Aufbau in German means to build up. It just means that we have to fill all of the first energy level shells before we fill the second. And we have to make sure the second is totally full before we fill the third, right? So that makes pretty good sense. Seems intuitive to me. So we have to start building down here and filling in our electrons. So we're going to fill in low energy first, and then we'll move towards filling high energy orbitals as we fill up the lower ones. So low energy to high energy. If I want to put these 2 electrons into this orbital, I have to follow the Pauli exclusion principle. Pauli exclusion principle, you can read it there, but essentially what it means is when I draw 2 electrons in that orbital, I have to make sure I reflect them as having opposite spins. So we know in general, every orbital, so one orbital, can hold 2 electrons. When those 2 electrons are existing together in an orbital, they have to have those opposite spins. So I drew crazy little pictures like this on the first slide, but they've simplified this notation. And so if we want to show opposite spinning electrons, the convention is I draw an up arrow with just a half arrowhead there to indicate there's a positive spin, and then a down facing arrow to indicate there's a negative spin. So if I wanted to assign m sub s to that up facing electron, my 4th quantum number, I would say, that's an equal sign, I would say he's plus 1/2, meaning he's spinning in the positive direction. So an up-facing arrow is indicating a quantum number of plus 1/2. And so the down-facing arrow, right, is telling me that in this orbital I have a down-facing or a down-spinning electron with a negative or oppositional spin. So those are my quantum numbers. All right, so if I want to fill up 2s, I'm going to use Aufbau principle. I'm going to fill up all of the first energy shell, which I just did. Now I can move to the second energy shell. I have to fill up 2s before I can fill up 2p. I want to fill up the lowest available energy state. I listed these guys, S, P, D, F, climbing up, because those are the relative energies between these subshells. S has a really low energy, P gets a little bit higher, D gets higher still. So when I'm inside of the second energy shell, I have to fill up S all the way before I can fill up P. So I need to fill in these 2 electrons. One of them's going to go up and one of them's going to go down. A positive spin and a negative spin. Okay, I said there were 3 rules, so we got 2 of them handled. The third rule is going to be used when I have multiple orbitals with the same energy. So P has multiple orbitals, right? It has 3 orbitals, and they're all the same energy. X, Y, and Z, right? They're oriented in space, X, Y, and Z. They're all the same energy. So this rule is called Hund's rule. Hund's rule says when you're filling sublevels other than S, electrons are placed in individual orbitals before they are paired up. Everybody gets their own room before they want to share, right? So if I have to fill in the p orbital or the p orbitals with 3 electrons, everybody's going to get their own room. They all have parallel spins, and by convention we all show them facing upwards. So this guy won't be spinning up and his neighbor then spinning down. They're all going to spin up, and so we show that by placing these up-facing arrows. All right, so I have just written out an electron configuration and an orbital box diagram following these new rules for nitrogen. Let's practice another one so that we can make sure we have all these skills in place. If I want to do chromium, now I need to go into the transition metals. So when I write the electron configuration for chromium, you could try this. Make sure you're getting the same answer I'm getting. If you're not, visit me in tutoring. Recall, when we leave 4s, we enter 3d, right? So just remember that. Go back, look at your notes for writing electron configurations. If I want to come up with an orbital box diagram for this, every one of these subshells is going to need a box. So I'm going to need boxes for every one of these letters. I'm going to need 1, 2, 3, 4 S boxes. I'm going to need 2 P boxes, and I'm going to need a D box. I'm going to list them from low energy to high energy. Okay, so just in the order that we wrote them, I'm going to put down those boxes. So there's 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. Okay, so I just list them as I wrote them in the electron configuration. They'll always be in the right order. I'm going to use all those rules that we just went over to put in these electrons. Aufbau says I start over here and I fill all the low energy shells before I fill the high energy shells. So I start on the left and I fill as I move to the right. Pauli exclusion says if I'm putting 2 electrons into an orbital, they have to have opposite spins. So there are those 2 electrons. Now I'm going to place my 2 s electrons. I have all of my 2 p's, but I'm still going to fill them according to Hund's rule. It's just a habit. Everybody got their up-facing parallel spins. Now I can go back and pair them up with their downs, and that's how I place those 6 electrons. The S subshell gets his 2 electrons. Now, oops, I jumped ahead when I was pointing. Now I'm here. I have 3p6, so I have 1, 2, 3, 4, 5, 6. Now I'm at 4s. So he'll go up and he'll get a down. Now I'm at 3D. I only need to place 4 of these. So I need to watch Hund's rule, which says everybody gets an up-facing electron before I ever pair anyone up. I've just placed those 4 electrons. No one in the 3D gets a pair. This is important because I said that spin is related to magnetism. If we have unpaired electrons, right, they don't have anybody sharing their orbital with them, then they have unpaired, they are also unshared, but that's chapter 9. They're unpaired electrons. They're all alone, so their spins are not canceled out by a neighbor, right? They don't have a down-facing electron in their orbital. Spins are not canceled out. So I have all these tiny little magnets spinning in directions, and all of their little magnetic moments add together, and these unpaired electrons make this chromium atom magnetic. So unpaired electrons make an atom magnetic. Now, we call magnetic atoms paramagnetic. You might see that on your homework. We call them paramagnetic, and that means they're magnetic. I don't know why they make us stick on a new word, but magnetic and paramagnetic mean the same thing. So on the homework, you might get a question that says, which of the following atoms is magnetic? You would have to write the electron configuration and then write the orbital box diagram and look for unpaired electrons. Unpaired electrons spinning in the same direction without anybody canceling out the spin makes it magnetic. We'll talk more about that as we go on. All right, so last slide here for this video. We're just going to sum up how we could mess up the rules. So if we mess up Pauli exclusion or Hund's rule or Aufbau, we'll come up with the wrong orbital box diagram. Now, I list my orbital boxes from left to right. They've just, in this one that I stole from the internet, they're writing their energy levels bottom to top. Same deal. I go left to right. They're just climbing upwards. I use boxes, right? And they use lines. No big deal. If I write 3 boxes for P, they're just writing 3 lines for P. They're just being lazy about drawing the rest of the box. Okay, so nitrogen, we said in the earlier slide, is 1s2, 2s2, 2p3. So if we were to draw an orbital box diagram or line diagram like we have here, this one contains an error. So this question says, what is wrong with this picture? There's something wrong. So take a look, think about how that looks versus what we've been drawing, and see if you can spot the error. Okay, so the error is that this guy got a down-facing electron before this guy got his up-facing electron. So this electron shouldn't be paired up with this up-facing electron. He should be over here all by himself. So this is a Hund's rule violation. Each orbital in a subshell is filled with a single electron, before any orbital is filled with 2. So every orbital there should have gotten their own. So there's the error in that orbital box diagram. So what's happening in this one? Where's the error in this one? Here we see that before the 1s is fully filled, they went on to fill the 2s and then the 2p. You must fill the 1s electron before you move on. So this guy's missing his down-facing arrow. That's an Aufbau violation, right? Aufbau says to build up. So you must fill in the lower levels before you can build up. And then lastly, where's the error here? This is a Pauli exclusion violation. Pauli exclusion says that if you have 2 electrons living together in the same orbital, they must have opposite spins. This is not a stable electron configuration. Electrons won't exist like that in an orbital. It's like having those 2 magnets that repel, right? We're not going to get these two magnets to live close to each other. We're not going to get these electrons to live close to each other. Okay, so now you have a sense of how to draw orbital box diagrams. You have the beginning of an understanding about spin, which is really important because it helps us understand how to fit electrons into orbital box diagrams. And these diagrams also help us figure out if an atom is magnetic or not, because it allows us to see if we're generating electromagnetic radiation that's not being balanced in the opposite direction. All right, so I'll post this video for you guys to watch, and then I'll put up the second video, and that'll give us a good head start into Chapter 8. We'll pick up on Chapter 8 when we get back together on Thursday, and your homework is posted, so you can go and practice those problems. I'll also try to send around a worksheet to you. All right, enjoy the weekend, and I'll see you on Thursday.